Hello, this is Miss Leminski. I'm one of the intermediate algebra teachers here at Edina High School, and I'm here today to teach you about section 10.2, the cube root function. So in the first section you learned this chapter, you learned about the square root function, and so we're going to do a warm-up to review what that means. So last chapter we actually talked about finding like the square root of 49, square root of 27, square root of 2, and so on. Now square root of 49 is a perfect square. It's just 7. Because really you're thinking about what times itself equals 49. And you guys know that 7 times 7 is that. The second question though is square root of 27. Now 27 is not a perfect square, but we can use the perfect squares. 1 squared is 1, 2 squared is 4, 3 squared, so 3 times 3 is 9, 4 squared is 16, 5 squared is 25, and 6 squared is 36. So what we do know about 27 is that it falls between 25 and 36, so the answer is between 5 and 6. Okay, so we could do the same thing with square root of 2. Again, that falls between 1 and 2, so it's some decimal, but it's just between 1 and 2. Now last but not least, we talked about square roots of negatives, and we said it's not possible because I can never multiply two numbers together and get a negative number. So it's not possible. No real solutions. So we've done that before, but today we're going to start talking about these things called the cube roots. Okay, so the difference is it's still a radical, but it's got a 3 as the index. So we're thinking about what times itself 3 times equals 27 in this case. Okay, so we called these the perfect cubes over here. We also have these are perfect squares, sorry. We also have perfect cubes. So 1 cubed is 1. 2 cubed would be 2 times 2, which is 4, times 2, which is 8. 3 cubed is 3 times 3, which is 9, times 3 more is 27. So by this we can say that the cube root of 27 is in fact 3. If we keep going, the 4 to the third power would be 64, and 5 to the third power is 125. And the reason I keep going is because in the second one, when I get the cube root of 72, that doesn't fall on my list of perfect cubes. So just like we talked about with the perfect squares, we'd have to figure out which two numbers it's between. And since 72 is between 64 and 125, I know that this answer is somewhere between 4 and 5. Cube root of 3, again, we can do the same thing, and we can see that it falls between 1 and 8, so it's somewhere between 1 and 2. Now, here's another very important thing about the cube root function. We said that we can never do the square root of negative 16 because two numbers times itself will never get a negative answer. Having said that, a cubed root, if I multiply a number times a number times a number, am I able to multiply 3 numbers together by themselves, so same thing times itself 3 times, and end up with a negative? Well, if I have a negative times a negative, that becomes positive, but if I multiply that by another negative, a positive times a negative is negative. So cube roots of negatives are in fact possible. Okay? So in this case, again, 16 doesn't fall on the list, but I can see that it falls between 2 and 3. So the cube root of negative 16 would fall between negative 2 and negative 3. Or if I asked what is the cube root of negative 27, it is possible. It's negative 3. Okay, so that's a little bit of a warm-up to introduce this idea of the cube root. The objective today is to find out the key features of the cube root function, and we're going to talk about translating the cube root function. The good news is this lesson is very similar to 10.1a in terms of the translating. We just have to learn what the cube root graph looks like. And the best way to do that is to make a table. Okay. Now the problem is we want to think of easy inputs. So yes, it is easy to take the cube root. So again, this is our function, the cube root of 1, which is 1. Cube root of 0 is 0. Cube root of negative 1, as we just discussed, is in fact negative 1. So that one's nice and easy. Now, we can pick any x values we want as inputs. But if I plug in 2, we just talked about, we're going to end up with a decimal, and 3 and 4 and 5 and 6 and 7. Okay, so those all give me decimals, so I don't want to choose those. Instead, the values that I want to input that are easy are the perfect cubes. It just makes my job quicker and easier, and those are the ones we listed. So the next easy one to put in would be 8, because I know the cube root of 8 is 2. And again, the nice thing about this function is we can also do -8, which is -2. Are there inputs that can't be evaluated? No, because again, cube roots we can take of negative numbers. So that's a big difference between the cube root and the square root. Okay, so then if you plot those points, you can see at the right, we actually get this graph that comes over here, goes up through the middle, and up and over. Okay, so what are the key features of this graph? Okay, domain, remember that's our x values. So which x values does the graph cover, or what x values can we plug in? And we just said we can plug in anything we want, which means it's all real numbers. So that's the answer in words. Now there's 2 different ways you're also going to be asked to show this. Inequality notation would be everything is -infinity is less than x, because it's domain, which is less than infinity. We've used that a little bit more this year. But one thing we haven't talked about for a long time is this thing called interval notation. The way we write interval notation for all real numbers is that, put a parenthesis, it starts at -infinity, goes to +infinity with another parenthesis. The reason I show that in this lesson is simply because when you go to do your homework, if your answer is all real numbers and it says to write the answer in interval notation, you want to make sure it looks like this. So make a note of that in your notes. Okay, so the range. Again, the range is what possible y values can you get out. And since I can keep plugging in all values, it goes all the way down negatives through 0 up through the positives, the range is also all real numbers. So again, if we wrote it in inequality notation, it'd be -infinity is less than y, because it's my y values, which is less than infinity. And in interval notation, it's from -infinity to infinity with parentheses. The x-intercept goes through 0, and the y-intercept also goes through 0. And the last thing that we want to know about this graph is that if I trace it from left to right, you can see that my pencil always goes up, sometimes slightly, sometimes more steeply, but it is always going up. So we need to know that the cube root graph is always increasing. All right, so those are the key features of the cube root graph. Now, just like with the square root graph, we can figure out maximums and minimums over specific intervals. Now, it does keep going up and down forever, so we'd have to specify the intervals in order to do that. So in order to do that, I would find f of the smallest value, f of -8. I'd take the cube root of -8, gives me -2. So this would be the minimum. And then I would do f of +8, since that's what they gave me as the biggest interval. The cube root of 8 is 2, which means that's the maximum. Why don't you go ahead and pause the video briefly and try number 2, and then play it to see the answer. So you should have done f of -27, taken the cube root of -27, which was -3, which will again be my minimum. And then f of +27 is the cube root of 27, which is +3, which would be my max. Okay, now we have to now talk about how do you translate the cube root function up and down. So the red graph is the original cube root of x, and my new graph is the cube root of x plus 4, and we can see that the plus 4 is not under the radical. So let's talk about what happens. Well, from the red to the blue, I went up 1, 2, 3, 4. You can see that from one key point to the other, same key point on the other graph, we went up 4. Just like you learned with the square root graph, if you have a cube root of x and you add a number on the end, that will shift it up that amount. If you subtract a number on the end, it will move it down that amount. can see those points move. So now, to write this as our notes, if we have g of x, cube root of x plus k, and it translates k units up, the domain, if we go back and look at the picture, it doesn't change, nor does the range. Here's the really nice thing about this graph. Okay, the domain is still all real numbers, or in interval notation, negative infinity to infinity. And the range, if I shift it up k, is still negative infinity to infinity, or all real numbers. Same thing, if I shift it down k units, so if it's a minus k on the end, then the domain is still all real numbers, or negative infinity to infinity. And the range is still all real numbers, or negative infinity to infinity. Okay, so that's translating up and down. Again, it's if you're adding or subtracting a number outside of the radical or on the end, because it's changing your outputs, your y values. Okay, now let's talk about what happens if we do something inside the radical. So you can see again, we're starting with our red graph, the cube root of x, and now we're translating it to g of x, which is the cube root of x plus 5. And again, the plus 5 is under the radical. And again, to get from red to blue, we can see that we go 1, 2, 3, 4, 5, but to the left. Okay, so you can see that all those key points translate 5 to the left. So just like we learned with the other graph, if it is inside the radical with the x, it affects the inputs, the x values, but it affects it the opposite of what you think. So it actually, the plus 5 moves it to the left 5. If it was x minus 5, it would move it to the right 5. Okay? Now if we look at this picture, again, we're going to answer domain and range. And again, the good news is that doesn't change. Whether you're shifting h units left with a plus underneath or shifting it right with a minus underneath, the domain and range are still all real numbers, negative infinity to infinity for everything. Okay, so shifting the cube root graph does not change the domain and range at all. Okay, so I want you to take a few minutes and pause the video, and next to each of these I want you to describe how the graph compares to the cube root of x. If you need an example, I'll talk through one first. Again, I see the minus 2. It is not under the radical, so I know that affects the output, shifts it up or down, and since it's minus, it's down 2. Okay, so pause the video, try 2, 3, and 4, and then play it again to see the answers. Number 2, you should have seen the plus 1 under the radical, so it affects the input, the x, but the opposite of what you would think. So it actually goes left 1. 3 and 4 are a little more challenging because there's two things that happen. First, in number 3, I see the x minus 4 under the radical, which means it goes right 4. But then I also see the plus 5 outside the radical, so it goes up 5. And then finally, number 4, the x plus 2 under the radical goes left 2. And then the minus 6 makes it go down 6. So that's what you should have gotten for those answers. To summarize, the question is, what are the key features of the cube root function? Okay, it's always increasing. The domain and range are both negative infinity to infinity, or all real numbers. And the x and y intercept are at 0. And then again, how do you translate it? It's the same rules as before. If it's inside the radical, it shifts it left or right, opposite of what you think. And if it's outside, shifts it up or down. Before you go, I want you to pause it on this last slide. These are the key notes that you should have. So if you didn't take notes as you went, I would pause it here and copy this down. Make yourself some nice notes about what we did. And if you did take notes, I would confirm that you have all of the things from this one summary sheet in your notes. Thanks so much. And now you'll want to go ahead and do your homework assignment for 10-2 day 1.